Hello everybody and welcome to lesson 15 on the Save My STEM Physics channel. Today we are going on to the second lesson for wave physics, so wave interactions, and it's going to be on refraction, refractive index, and Snell's law. So, first things first, what is refraction? Refraction is, if I just put a heading here, refraction is change in direction, change in speed, and change in wavelength of light when it passes through a boundary. So if I repeat that again, refraction is when light changes direction, speed, and wavelength once passing through a boundary. So that's all refraction is. You can think about it in terms of a glass block, which is something that comes up very frequently in physics. If you imagine this is our glass block, as light enters at this angle, it is going to start to move a little bit more like that, which is something we'll get onto shortly, and then it will leave, assuming that these were parallel, it will leave at the same angle it entered at, which is again something that we'll get onto very shortly. So this is all refraction is. The frequency notably doesn't change in the light, because the frequency at the boundary is going to be the same as the frequency inside the boundary, because the amount of wave cycles entering and exiting and inside cannot change. The number of wave cycles is the same. So again, if we think about that in terms of our equation, c equals f lambda, speed of light equals frequency times by wavelength, the way that we know that the wavelength is increasing is if the wavelength is decreasing, if the speed goes down and the frequency stays the same, then the wavelength must go down accordingly. So those are sort of the ways that to remember how waves interact when they refract. And now to get onto the actual physics of it with something called Snell's law, and then we'll go over refractive indices and then we'll get into Snell's law. So what is a refractive index? There are two types of refractive indices. There are absolute and relative. And the refractive index just measures how much the speed of a wave changes upon entering a new medium. So like a new medium is a glass block compared to air, so air into glass or glass into water. That's all refractive index is. And the absolute refractive index is measured by doing the speed of light in a vacuum, which is in your data booklet, it's 3 times 10 to the 8 meters per second, and you divide that by the speed of light in the medium, which is denoted by C subscript S. So, if I say that this glass block is in air, the glass block is in air. Air has a very, very close refractive index to a vacuum, so we assume the refractive index to be 1, because if you think about it like this, 3 times 10 to the 8 over, it's going to roughly be travelling at the same speed, 3 times 10 to the 8 equals 1. Therefore, the absolute refractive index of air is about 1. So, if the speed of light in the air is 3 times 10 to the 8, and then we say it slows down to about 2.5 times 10 to the 8, we're just going to do 3 times 10 to the 8 over 2.5 times 10 to the 8, and that's going to land us about 1.2. In fact, exactly 1.2. And and so that's what the refractive index of this glass would be. Now that's not an actual very accurate value for the refractive index of glass. The refractive index of glass is closer to about 1.33. But yeah, so absolute refractive index is measured from the speed of light in a vacuum compared to the speed of light in the medium, but relative is medium to medium. So we will denote that with C1 over C2. And that's kind of what I did with the air and the glass there, is the relative refractive index. But because the absolute refractive index of air is so close to that of the refractive index of a vacuum, it's kind of the same thing in the example that I gave. And now that we know what refractive index is, refractive index notably is denoted by the letter N. So we can have N glass, for example, or N air, right? And air, as we said, would be about 1. N glass would be about 1.33. And now we're going to get on to using uh, refractive indices through something called Snell's law. So during refraction, and I believe this is, yes, this is in the data booklet. It's not called Snell's law. It's called the law of refraction, I think. You'll have to check for yourself. It's under the waves section. Should be easy enough to find. And it is n1 sine theta 1 equals n2 sine theta 2. And what that means is the first refractive index, so I'm just going to put first R index, and then I'm going to put at the top here angle of incidence, so the angle it enters at. You can guess that that's the N2 is the second refractive index, and this is the angle of refraction. For those of you who don't quite remember from GCSE, if we go back to our glass block example here, the way that we measure the angle is we draw an imaginary line called a normal. You see that dashed line there? We draw an imaginary line called a normal, and which is perpendicular to the surface, and we measure the angle between the ray and the normal. And again, if we continue our normal on this side, the new angle would be measured there, right? So getting back to this equation, that's how I know that if it's going from air into glass, that the angle on the inside is going to be smaller. So if we rearrange this, so if we take the fact that that N1 is less than N2, right? N1 sine theta 1 equals N2 sine theta 2. If we rearrange for theta, we're going to divide by N2, and then we're going to do sine inverse of both sides, so that we're just left with theta 2. And N1 sine theta 1 over N2, and then we do the sine inverse of that, or arc sine, some of you may call it. And we're going to end up with that. If we know that N1 is smaller, the sine theta 1 is just going to make it even smaller, right? So then we're going to get sine inverse of something smaller than what would be rearranged in the other way, and therefore theta 2 is going to be smaller than theta 1. So if I sort of show you, I sort of said a bit of a mess there, sorry. If we were to rearrange it the other way, we would get n1 equals n2 sine theta 2 over oh no, sorry, theta 1 and then sine inverse. And so if we compare these two, because n2 is greater, even though the sine theta is going to make it smaller, the inside on this one is going to be smaller than the inside on this one. so theta 2 must be smaller than theta 1. I hope that makes sense, because I did kind of say it a little bit rough around the edges. And I think that is it for Snell's law. I think that's it for refractive index, and I think that's it for refraction. Refraction, in and of itself, is a little bit of GCSE recap. Obviously, refractive index and um, Snell's law are new information. So thank you very much for watching. Hope this video has been helpful for your understanding of the topics, and I will see you all in the next lesson.